let's start the presentation. Okay, so my presentation is about Tide and exploring WebSocket with Tide. So first, let me introduce myself, who I am. My name is Javier. I'm a system engineer and open source enthusiast. I am from Buenos Aires, Argentina. And in the past, I have been working mostly with Node.js and Python. And I started learning Rust around 2 years ago. This talk is about Tide and WebSocket. So first, we want to talk about Tide itself. It's a fast and friendly HTTP server framework for async Rust. And Tide has a built-in support for server-sent events, but doesn't have built-in support for WebSocket. So when the HTTP/RS team announced the support for the experimental release of the Tide WebSocket crate, I think that was awesome. And I started just experimenting with that. And there was a really fun tagline about this crate that is just open a socket. I thought that it was really great. So that was around the end of the last year. So I started playing with the setup. And as you can see, there's two ways that you can use or handle WebSocket in Tide. You can use it as a middleware, or you can use it as an endpoint. And in both cases, you receive the request and the WebSocket connection. So you can waiting the message in the connection, looping using a while loop to iterate over the next, calling next, and I wait. And you can also send to a client using, in this case, in the example that I take from the Tide WebSocket repo, and they are using the send string, but there is also another method to send other kind of information to the client. And you can also use it not as a closure. You can use it with a function, for example, like this. This is the same behavior that we saw earlier, but handling the WebSocket connection in a different function, if you want to use it this way. That is the basic setup. And let's try some exploration right now. So I have a couple of examples here. The first example that I made is like a tic-tac-toe game, but just playing with the name, tic-tac-tide, where you can see that you can just like start games. Let me just how this work, and just let's just win really easy. It's not. So as you can see, we can handle this kind of games, or you can build cool things with WebSocket around Tide, and that for me is really awesome. Let me go back to the presentation. And the second exploration that I made is create like a mimic of this Socket.io homepage, where you can see the stream of tweets related to, in that case, Socket.io. So I create a mimic that you can see the streams of tweets related to different rooms that I call rooms, but these topics. For example, I really love basketball, so I have like the NBA room where I see all the tweets related to the NBA teams, and you can see, I don't know, like Rust room, where you can see tweets related to Rust itself, the HTTP/RS team, or the Rust Foundation, and just one for the Rust DC for this presentation. Let's try this, just creating a tweet and see if we can see this in the room. But I don't know if the API will just show, but when the tracking system just collect that tweet, it will appear here in the room. I think this is awesome because you can thinking more about how to build around the Tide WebSocket. And as a wrap up, because it's aligning Tide, I don't want to just borrowing a lot of time. The wrap-up is that you can use as an endpoint or as a middleware in Tide. And there is a different send method that you can use for sending information to the client, like send JSON, send a string or binary information. And there is a lot of room to build on top of this. I think it's a really foundation for building cool things around Tide and WebSockets. That's me. You can find me on GitHub. I'm Javier Viola on GitHub and Twitter, and labs.javierviola.com is the site that I will continue share all this exploration around Tide and WebSockets. That's it.
How easy is it to kind of slot in this might be too broad, so feel free to tell me it is, and I'll take it offline, but how easy is it to slot like a Rust WebSocket server alongside maybe an existing, like maybe more traditional, like Python or Rails-ish kind of application to manage WebSockets, do you think?
It's a really good question. I think the support is there for the basic connection of WebSocket. I think it should be pretty awesome to build like a support for Socket.io client, for example, because for me, it's the most used WebSocket client and server also use it in the web. So handle, but it's a little bit custom. It's not like just WebSocket that they use, but if you can build on top of the Tide WebSocket support for that kind of clients, should be really easy to just switch from, I don't know, from Node.js or from Python or from Rails to use Tide WebSocket, because it's really ergonomic and it's really easy and fun to use.
Cool. One more question before we move on. In the chat, and now it's, there we go. What Twitter streaming library did you use or would you recommend?
I use one that is Twitter Stream that have like simplified methods. There is another one like called X or something like that, that is more robust library. But for this purpose that I was only want to connect to a Twitter streaming API, was really easy to use.
Thanks for having me. I will go ahead and share my screen. If I can, I'm in Teams all day, so I have to remember where the buttons in Zoom are. There you go. And let's share this one. All right, well, hello, Russ DC. It's great to meet you. I was a little amused I looked at the back chat in Zulip, and someone was asking if I was local to the DC area. No, I'm in Seattle, the other Washington. However, I do volunteer with the Marine Corps Cyber Auxiliary, so I have been out to DC a few times. I was at the giving a talk in the Pentagon at the very end of 2019 before lockdown happened, and Virginia in December is something, all right? It's very different from Seattle in December. So let's go ahead and get started. When I work with someone who is just learning Rust, I find they sometimes question whether the Rust borrow checker is their friend or their foe. If you take a look at the Rust subreddit, it's common to see posts with headlines like this. Newbie question regarding the borrow checker. Help fighting the borrow checker. And does it ever get easier fighting with the borrow checker? However, as you watch people get more experience in Rust, they tend to come around to the borrow checker and realize what it protects them from doing. So in answer to the question, is the borrow checker a friend or a foe? I say the borrow checker will become your friend through experience. And along with gaining experience with it, it is also very helpful to understand how it works and why it does the things it does. We're going to dive deep into that, but before we do, briefly cover who I am. As was introduced, I'm a principal software engineer at Microsoft. Prior to Microsoft, I was at Mozilla working on Rust full time. I unfortunately was caught in the layoffs that occurred last August, but it meant I was available when the call came from Microsoft. I am a board director of the Rust Foundation. I'm Microsoft's representative on it and lead editor of This Week in Rust. If you're not subscribed, I hope you do. And if you write something cool about Rust, please submit it to the newsletter. And to set expectations, we will first do a bit of a background on the Rust compiler in order to put the borrow checker in context. Then we will do that deep dive on the borrow checker. So let's go ahead and start with an overview of the Rust compiler. And let's take a look at this code example. This Rust function declares a vector composed of the integers 1, 2, 3, 4, and 5. After it declares this vector, it then uses a for loop to iterate through each integer in the vector and print it out on a new line. So if we were to run this in our terminal using cargo run, as expected, we would see the numbers 1 through 5 printed out on the screen. This seems pretty simple on the surface. Cargo builds and runs this piece of code for us. But there is a lot that happens underneath the surface in the compiler when Cargo is building it. There are 5 general stages to compiling a piece of code. It starts with lexical analysis of the code, then parsing of the code, then semantic analysis of the code. This is where the borrow checker comes in. Optimization of the code, and finally code generation, where the compiler creates the executable binary of our code. When we look at the stages laid out in a list like this, it might seem like they will run linearly. And in some compilers, they do. However, if you've delved at all into the Rust compiler internals, you might be thinking, hopefully not tweeting, but you might be thinking, wait a minute, isn't the Rust compiler at least partially query-based rather than linearly based? And the answer to this question is yes, but that is out of the scope of this particular talk. For the sake of clarity, I'll speak to the internals of the compiler as if they were functioning linearly. However, if you want to delve more into how the Rust compiler is query-based and what that means, check out the guide to Rust C development for more information. This guide has been a big help to me as I've learned how to hack on the Rust compiler. I'll give people a moment just to see the link, though I'll be putting it up on other slides in just a bit. All right. Going back to the stages of compilation, let's start with this first one here, lexical analysis. During lexical analysis, a program within the compiler called a lexer takes the raw Rust source code called a lexeme and analyzes it, and then splits the code into tokens to make it easier for the compiler to parse. And that brings us to the next stage of compilation called parsing. In this stage, a program within the compiler called a parser analyzes the tokens generated by the lexer and translates them into an abstract syntax tree, or AST. Having the tokens in this AST data structure makes it much quicker and easier for the compiler to do the rest of its work. And then at this stage, before it moves on to the next stage of compilation, the Rust compiler takes the abstract syntax tree that was generated by the parser and first expands any macros included in the code. So looking back at our code, let's take a closer look at this line, print line. Print line is a macro, which means when we expand the macros in the code, or when the compiler expands it, this line will be expanded to look somewhat like this. This is what the full print line macro looks like and how it would be represented in the abstract syntax tree. The other thing the compiler does at this point is de-sugar some of that syntactic sugar that makes writing Rust so delightful. For example, let's take a look at this for loop. In Rust, the for loop is a piece of syntactic sugar for an iterator. If we were to de-sugar this section of the code, it would consist of both a match statement and a loop. The functionality of this code is identical, but it's harder to read for a human. De-sugaring it like this makes it harder to read for a human, but it makes it easier for the compiler to understand it and optimize it. And then the third thing the compiler does at this point is resolve any imports in the code. So if you were bringing in an external crate or using internal crates or modules, those would be resolved at this point of compilation as well. Next, after all these steps, the compiler takes that abstract syntax tree and converts that AST into higher level intermediate representation. This is the next stage of compiling Rust code. This is also known as HIR. And let's pause here and take a closer look at the data structures that make up the HIR. It helps to understand them, knowing the data structures that make up this particular structure. So the first is a node. This corresponds to a specific piece of code. This is identified by an HIR ID, or some people say here ID. And that node belongs to a definition. A definition is an item in the crate we are compiling. These are primarily top level items within the crate. So this is identified by a def ID. And a definition is owned by a crate. This is the crate we are compiling with Rust. The crate structure stores the contents of the crate we are compiling, and also creates and contains a number of maps and other things that help organize the content, again, for easier access throughout the compilation process. This crate is identified with a crate num. And this is the original source code, Rust source code we are compiling. And let's take a closer look again at this section, this for loop. The for loop iterates through the numbers vector. Remember, this for loop desugars into a match statement and a loop. If we were to take a look at the node in the higher level intermediate representation, or HIR, that represents this match, we would see something similar to this. And again, this is a little hard to read for humans, at least it is for me. So let's go ahead and break this down. The arm structure represents a single arm of the match statement that our for loop desugared into. Match statements have multiple arms. And within this arm, we first have an HIR ID for this piece of code. This identifies a node within the HIR. And that node is owned by a definition. The definition is some top level item in the crate. And that definition data structure is owned by a crate data structure. So our for loop is a node within a definition within our crates. That's how we can identify where this node corresponds to in our original code. What also helps us do that is what is called a span. This stores the file path, line numbers, and column numbers of the original source code before it was desugared, before the macros were expanded, before it went through the stages of compilation up to here. This will be very important in the future as we continue to optimize and desugar this code. If we encounter a problem with the code after it is desugared and optimized, we still want to be able to show the user where in the original source code that the error was generated. If we were to return an error and show them the desugared code, which is different from the code they wrote, it likely wouldn't mean much to them. The compiler then takes the HIR and lowers it into the mid-level intermediate representation, also known as the MIR. This is the next stage in compiling Rust code. The MIR is constructed as a control graph. The units within this graph are called basic blocks, which are identified with values like BB0 and BB1. Within these blocks, each has a sequence of statements that execute in order. The very last statement is known as a terminator. This controls when and how the program proceeds to another basic block. This is a pretty simple example. There's only one direction the basic blocks can go. However, if our code had an if-else statement like this, if a condition is true, we do one thing, else we do the other thing, then the terminator, a BB0, would have the option to either proceed to BB1 or BB2, depending on whether that condition is true. In this case, there's more than one path that the program can take when it encounters the terminator in BB0. There are definitely more data structures involved in the MIR, and if you're curious, again, check out that guide to Rust development. It's a hugely helpful resource. Let's go back to our desugared code, and let's focus on this match statement, which is assigned to a variable called result. If we looked at the MIR for this particular piece of code, it would look similar to this. Now, I've simplified this for the sake of appearing on a slide. Up here in the top left, we have our basic block identified as BB2. And then we have what is called a local. A local in the MIR represents a place in memory, or more specifically, a place on the stack frame. In this case, _5 corresponds to the value of the variable result. And like in the nodes in the HIR, we have a span, the piece of the original Rust source code that each node in the MIR corresponds to. Again, if we encounter an error when we're operating within the MIR, we can still easily refer to what lines in the original source code caused the error and return that error to the user. And that brings us to the third stage. This is big in the Rust compiler: semantic analysis. This is where the compiler tries to figure out what the programmer is trying to do in a way the compiler can understand it and then translate it into machine code. And at this point, after it's lowered into the HIR and the MIR, at this point of semantic analysis, the compiler will run several checks, including the borrow checker. And we'll come back and take that deep dive into the borrow checker in just a few moments. But for now, let's focus on these last two stages of compilation: optimization and code generation. These stages are where the code is transformed into an executable binary. And the Rust compiler, we use LLVM to do this for us. LLVM is a commonly used collection of modular and reusable compiler and toolchain technologies. The Rust compiler uses it to further optimize the code and generate the machine code to run it. Before it uses LLVM, the Rust compiler takes that MIR we created earlier and lowers it again into the LLVM intermediate representation, or LLVM-IR. This prepares it for processing by LLVM. And as far as I'm concerned, the LLVM-IR is pretty darn unreadable, but it looks something like this. And you can see that it's still organized into basic blocks like in the MIR. We then use LLVM and pass it the LLVM-IR, and then it runs more optimizations on it and emits machine code. And then it links the machine code files together to produce the final binary. So that means when we run cargo run, we see these numbers printed out because of all those compilation steps. So yay, that gives you a bit of an idea of how the compiler works to take your Rust source code and make it something a computer can execute. And at this point, I do want to go back and take a deeper look at the borrow checker. And for this part of the presentation, let's use a different piece of code. Now, I want to say right up front, if you're looking at this code and thinking this will error out, you are right. And we'll see how and why that happens in just a moment. But first, let's go through this code line by line. We declare the variable x and give it the type string. And then we set the value of x to the string hi cloud native Rust day. I am given this presentation there on May 5th, so they are included in my examples. And then we say that the variable y's value is equal to the value of x. And then we attempt to print both variables x and y. If we tried to build this code in its current state with cargo build, we would get an error. And this error is the result of the borrow checker. Let's go through how the borrow checker identified this error. The borrow checker does several things, including tracking initializations and moves. How this plays out in our code is when we start with this first line where we declare the variable x with the type of string, x is not actually initialized yet. It won't be considered initialized until it is assigned a value. If we look at the MIR for this line of code, we see that x is represented by the local _1, and the local _1 is assigned the type of string. Now let's look at this next line of code where we create and assign it the hi cloud native Rust day string. Now that x has a value, it is considered initialized at this point. We create a new place in memory, local _2, where we store the hi cloud native Rust day string. Then we move the value, emphasis on the word move, stored at _2 to _1. Remember, _1 corresponds to the x variable. So we have created the string in memory and moved it to be the value of x. Now let's look at this line where we attempt to create the variable y and assign it the value of x. This line is where the value of x is moved to y. If we look at the MIR created for this line of code, we see that y is assigned to the local score _3. Remember, a local represents a place in memory. And _3 is given the type string. Then the value at _1, remember that represents x, is moved to the value of _3, which represents y. This means when we get to here, when we try to print x, x is not initialized at this line, so we cannot print it. And that's what generates this particular error. We're attempting to use the value of a variable after that value has been moved. Something I'd like to specifically call out is how the compiler shows where the error was generated from in the original source code through a span. Even though we had lowered this code to MIR, or mid-level intermediate representation, we still tracked what items in the MIR corresponded to what places in the original Rust code. This is very helpful to the end user. What is also helpful is this. The Rust compiler not only tells you what the error is and where it is, it also gives you a command to get even more information about the error so that you can fix it. If we were to run this command, we would see not only an explanation of the error, but also a piece of example code that would generate it. Then the message gives you even more information about how to fix it. This suggests using a reference to borrow a value rather than attempting to move the value. There's a difference between borrow and move, which we saw done in the MIR representation of our code. So let's follow this recommendation and change this line so that y is assigned to a reference to the value of x rather than moving the value of y into, or value of x into y. If we ran the code with cargo run at this point, once the compiler builds the code and executes it, we would see the message, "Hi, Cloud Native Rust Day," printed out twice. Once is the value of x and once is the value of y. Rather than fighting the borrow checker, we used it to make our code even better. Along with tracking initializations and moves, the borrow checker also deals with lifetime inference. Let's go over what that means. Rust uses the word lifetime in two distinct ways. The first is to refer to the lifetime of a value. That's the span of time before the value gets freed. Another word for referring to the lifetime of a value is referring to the variable scope. Let's see how this plays out in our code. And let's start with this first line where we assign the value of x to be this string. At this point, x is live, its lifetime begins here. When we get to here and move the value of x into y, we've gone back to the code that will error out. If we move the value of x into y, this will end x's lifetime. Which means when we get down here and try to use x again, x is dead. Its lifetime is no longer in effect, which is why this program would error out. The other way Rust uses the term lifetime is to refer to the lifetime of a reference to a value. This is the span of code in which the reference can be used. Let's look at our corrected code, where we assign the value of y to be a reference to the value of x. If we look at the MIR for this line of code, we remember that the local _1 refers to x, and the local _3 refers to y, and we see that the _3 local is assigned a reference to the value of _1. Going back to our code, let's alter this slightly. And let's try to drop the value of the variable x before we try to print the value of y. If we do this and then run this code, try to build this code, we get an error. We can't drop x because it is borrowed, and that borrow is used later. The borrow checker tells us that x, because it is referenced by y, needs to stay alive for at least as long as y needs to stay alive. X's lifetime must be greater than or equal to y's. Looking at this in the code, Again, this is X's lifetime. And this is what needs to be the lifetime of Y, which is a reference to X. Notice that even though they overlap, X's lifetime ends before Y's lifetime is supposed to end. Y can no longer reference the value of X after this line. So at this point, along with X, Y would be dead. In order for this code to compile, the lifetime of X must last at least as long as the lifetime of Y. The overarching way the scope and the lifetime of a reference relate to each other is that if you make a reference to a value, the lifetime of that reference cannot outlive the scope of the value. As I wrap things up, I want to make sure you know there is so much more to the Rust compiler and the borrow checker. Again, and I noticed someone already put it in the Zulip, check out that Rust C development guide if you'd like to know more. It's a fantastic resource. Going back to this question from the beginning, is the borrow checker a friend or a foe? Well, I say it's a friend, though a very strict one. But the best thing about this friend is it will not only tell you when something is wrong, it will also tell you how to fix it. And I find that to be one of the best qualities I can find in a friend, as well as one of the best qualities I can find in a compiler. Thank you. All right, let me unshare my screen. If I can find the window. There we go.
That was awesome, Nell. Do people have any questions? I know I have questions, but
Yeah.
I want to hear other people's questions.
I had one. So where exactly does the borrow checker fit into the steps of the compilation process? Is the borrow checker operating on the mid-level representation, or is it kind of separate from the compiler?
It's operating on the mid-level representation. Semantic analysis happens right after we lower the code to the mid-level representation. I believe that is the case, at least.
Got it. Cool. Thanks. And thanks for the talk. Awesome.
You're very welcome. And along with questions about the talk, I'm happy to answer questions about the Rust Foundation, This Week in Rust, anything that might be on your mind.
I was curious about the, so I know there's, and I forget which one it is, but there's like an alternative compiler toolchain under development, I think in C++ for Rust. And one of the ways that they're able to do that, you know, and it's not the biggest project, you know, aside from the Rust compiler itself, is that they are skipping the borrow checking. They assume that you've already validated this. Is that like, I guess it's like, would that benefit like a Rust build if you said like, okay, I know this has already been checked into CI and everything, and I know you can skip the borrow check on this when you're, you know, building it for like, you know, like in a CI environment or something like that? Or is it like, oh, well, we already have to do all of the work to get this information available for the borrow checking? And so like, would you see a benefit in compile times if that were an optional step?
Right. If it's code that, you know, you check in the code, CI runs the full build using the Rust compiler toolchain, says it's fine. I could see, and then runs tests on it, checks that everything else is fine. I could see there being a benefit to running it without the borrow checker, provided you know the borrow checker has already run. One of the big criticisms we get about Rust is the compile times are very long. That could be a way to reduce the compile times when you're releasing something into production. So yeah, I could see a benefit to that. Borrow checker does eat up a lot of the compile time. I don't think it eats up all of it. I think there's some other things in there too, but yeah, I could see that being beneficial if the code's already been checked previously.
I know a couple of the biggest things in kind of the direction of Rust that have been changing have been efforts towards like async and Tokyo and getting that kind of released, which is amazing. I was wondering if you had any insight on kind of what the next big moves for the Rust community are going to be?
Sure. So I wrote the RFC for adding streaming functionality to the async functionality in Rust, and that was a 6-month process. So that did get approved, and I think it's an unstable feature in the language now. Where I see that expanding. Everyone and their mother seems really interested in async, especially Amazon, and Amazon has hired a good. Amazon and Microsoft and Google hired pretty much all the people who were laid off by Mozilla. And so there's a high interest in that. I do think on a technical side, we're going to see much more focus on the async ecosystem in the language. On the, I don't want to say non-technical, but on the more the community side, a big reason for the founding of the Rust Foundation was figuring out a way to support maintainers to make creating all this code for the people who are not supported by their employer in working on Rust full time are able to do that and hopefully not burn out. That's a toxic cycle we're trying to break. Oh, they Polonus. So when I was putting this talk together, when I was still at Mozilla, I said to Nico Matsaki, I want to do a talk on the borrow checker. He said, oh, I did one, and I was introducing the concept of Polonius. I don't know if there's work ongoing with Polonius, but it is, you could say that it is an alternative to the borrow checker that does some of the same things. It's very early age, or very early, but it looks pretty cool. I don't know a ton about it specifically, but I definitely have heard the name come up.
I was curious how much of what you were, presenting would have been different if you had presented it before. Would it have been different before you presented it, before the non-lexical lifetime work was added to the compiler, or is it those concepts not touching what you were presenting?
I think there would have been a difference. I'm not hugely familiar. I know that the changes for the non-lexical lifetimes came in. I'm not hugely familiar with what was there before then, so I'm not sure what would change, but I have no doubt that some things would be changed, yes.
When you were putting together this talk, obviously you've already had kind of the experience diving into the various parts of the build toolchain, but was there anything that stood out to you as like particularly surprising, or something that wasn't really operating the way you thought it would operate based on kind of higher level understanding of things?
Right. Well, the first thing I learned when I started compiler hacking, and I learned this the hard way, is don't build the entire compiler every time you make a change. It was taking 40, 50 minutes on my very well-equipped Dell XPS laptop. So I learned, and there's a lot in that guide, the Rust-C guide, how to build it in stages or build only the stage that you need at the time you need it. The thing that still blows my mind, and I didn't go into it in this talk, is the way the query-based compilation steps work. I'm very intrigued by it. I don't fully understand it yet, but the idea that we don't have to run all the steps linearly, we can run steps only when we need to run them, is something I'd like to dive into more. So I think that's what surprised me the most.
Hey there, I have a question about the Rust Foundation. So with the stand-up of the Rust Foundation, is there going to be any changes in how people can get into contributing to the development of Rust, either the compiler itself or any core projects?
There won't be. The Rust Foundation exists to support maintainers, in that's helping them continue doing their work. The technical decision making and the bringing new people into the project, etc. That authority resides solely within the Rust teams that already existed. What I would like to see the foundation do is do some educational activities for this is how you hack on the compiler, and this is how you get into Rust. So I could see that, but as for changing the workflow of the teams, I don't see it changing it at all.
Okay, thank you.
On that note, do you have any suggestions for anybody who's interested in making like their first contribution to the Rust compiler, where they might start looking?
Yeah, I would go into the compiler team Zulip channel and ask, are there any good first issues or any good issues people would be willing to mentor on? And they definitely are. They've done that for me at least a few times now. I would start there because I was trying to go through the issues in the backlog of the Rust compiler and I was completely lost. So yeah, I would start off by asking the Rust compiler team. They're very nice people. I've never seen them call anybody a noob, and ask what issues they would recommend.
There was a question in chat.
Are C++ compilation times faster or similar to Rust? They are faster because they don't do all the borrow checking. And the reason Rust exists is when you're writing, a question I get a lot is, why would I have my developers learn Rust when I can just hire C++ developers who know what they're doing? Okay, number one, condescending as heck. Number two, the historical problems with C++ has been around for a long time. The reason it's so but the problem is it's very easy to introduce memory bugs in C++ that lead to things like segfolds, null pointers, etc. I didn't fully understand this until I started taking a C++ course on Coursera last year. And with how Rust is different is it has the borrow checker, it has the built-in checking for all those potential memory safety issues. So if you have one in your code and don't realize it, and like I tell people, the Microsoft Office code base is mainly in C++, it's 250 million lines of code. No one's able to keep all of that in their head or see potentially all the downstream effects of a change in a single piece of code. So the Rust compiler will not let the code compile if you have those memory safety issues. Esteban Kuber, who's a member of the compiler team, he put it this way: in the C++ compiler, a feature is considered complete if you can do it successfully. In the Rust compiler, a new feature is considered complete if there's no way that you can do it wrong. So yes, Rust compile times are longer due to the checking that's involved. But for a lot of people, the longer compile times are worth it to ensure there's not those memory safety issues in their code. Also, my C++ class, I learned about deep copies and shallow copies, and I could not sing the Lady Gaga shallow song anytime I was trying to create a shallow or a deep copy.
Is that a disqualifier or?
The long disqualifier for what?
I mean, does that sway you either direction? Does that at compilation times it's you need to finish the song before you finish the part?
That's funny. With the C++, I never got through the chorus. With Rust, I mean, well, with the whole Rust compiler, I could get through the whole soundtrack probably if I was trying to compile the whole compiler from beginning to end.
Hey, Nell, I have a question on This Week in Rust.
Yeah.
So, first of all, big fan of the newsletter. One of the few that I read every time. Do you have any plans for it? Like, is there going to be any changes in focus on it, or is there anything you'd like to add to it? Where do you see This Week in Rust going? Do you like what it's become? How can the community help with that?
Sure. I do like it a lot. People seem to respond well. There's been some changes to the formatting based on comments from the community, and they've been really helpful. One of the criticisms we get a lot is that in the job section, which I depend on people submitting the jobs either on Twitter or through a GitHub PR, a lot of the companies that have budget to hire Rust developers are blockchain related companies. Not all of them by any means, but a lot of them are, and many more blockchain companies were submitting their job openings to This Week in Rust than non-blockchain companies. So it was kind of giving, it was giving a skewed view of what Rust is used for. If community members want to see different kinds of jobs listed, none of us, the editors, it's me, Colton Donnelly, and Andre, whose last name escapes me at the moment, or Andre Bogus, that's his last name. We don't have the bandwidth to search job sites to find other Rust listings to put, but if people want to submit those, I would welcome it. Same thing with events. I checked the Rust community events calendar, and that's often not quite up to date. I always go to the meetup page to check whether the meetup is actually happening or not. It saves me a lot of time when meetups come to the newsletter and put the posting in themselves when they're able to. So that helps. And my last piece of advice is don't ever think that a blog post topic is too basic to be included in This Week in Rust. We have Rust developers from the very, very beginning to the expert level Rust developers, and then people with different backgrounds, different programming experience. I came from the Ruby world. I came to Rust from there. That's very different from someone coming from the C++ world. So every perspective that we have is very valuable. And even if you don't think the majority of Rust developers will learn from your perspectives, Ruby to Rust representative, there's a lot of Rubyers who went to Rust. There's definitely someone who needs to hear your perspective on it, and that might help them understand this concept in a way they wouldn't have otherwise.
First of all, thanks for the talk. That was great.
You're welcome.
My question is, do you have any tips or guidelines from other projects you can point to on processes for auditing unsafe sections?
That is a really good question, and I don't. If you find some, please write it up and submit it to This Week in Rust. I would love to learn more information about that. Does anyone else know of any tools like that?
Basically, what I'm doing is like looking at it and trying to convince myself that this is right and reasoning through it. But I was wondering, yeah, if anyone's got better processes, and obviously writing tests, but yeah.
I mean, I suppose you could take the unsafe block out and see if the compiler errors on what you expected to error on. But does anyone else have perspectives on that or recommendations?
Also, have you used Miri? Is it something that you could? I haven't used Miri, but I understand that people have found issues in unsafe code using it.
I haven't used that. What is it called?
It's MIRI. It emulates the memory environment, and so it runs the Rust code in a interpreted emulated environment and checks for I think memory accesses that violate right, like I'm now like getting to the edge of my it looks really cool.
It does look really cool. I just pulled up the GitHub project.
No, this is awesome. Thank you.
One last question, if anyone has one.
Instead of I might have one. So when you if you change the actual platform target, like say you're targeting WebAssembly, does that change the compiling workflow at all?
I believe it does, but I couldn't quite tell you how. But now I'm curious, and I'm going to have to look into it.
Okay. RTFM.
Awesome. Yeah, well, that was really great. Thank you again so much.
You're very welcome. And I hope to, whenever we can meet up in person still again, when I'm in DC, to come by a meeting and meet you all in real life.
That would be fantastic. Yeah, that would be amazing. Cool. Also, thanks, Javier, again. I will be looking at that demo. That was cool.
Great, thanks.
Yeah, definitely. And then also too, something I forgot to put in the announcements, we may try to do another workshop event. So if there's, Barney had mentioned some of the memory issues. So if there are any other concepts that like you're working through and you would find useful in a workshop format, ping like me or definitely Dan on the Zulip, because we'd like to know what those are. But otherwise, yeah, thank you so much, everybody, for coming. Hope to see you next month and in the future.
Take care, everyone.
See ya.
Thanks.